Radicals are molecules that have an unpaired electron. Electrons act like little magnets. Normally they pair up, so that sort of the north end of one aligns with the south end of the other, so that these two electrons, one here and one there, flying around in that orientation together, are slightly less reactive. When you take one away and you have just one unpaired electron, it's incredibly reactive. It will stick to the first thing that it comes across. These radicals are truly radically reactive. Now, not all radicals are in a special class of molecules. They're all in a class of very reactive molecules. But not all radicals are equally reactive. The lone electron, the unpaired electron in a radical, exists in a p orbital, so it's flying around, smeared out in space in the wave, the standing wave of a p orbital. And we've seen already how these p orbitals can spread charge out when they're next to sp3 orbitals. The p orbital, the lobes go up and down. If you had an sp3 orbital, so say for example we have this p orbital here, the lone pair with the p orbital, right next to it in the carbon you have sp3 orbitals. This carbon is sp3 hybridized. And what that means is it has 4 sp3 orbitals arranged tetrahedrally in space. Now, 3 of them don't align with this p orbital at all, but one of them has a sort of sp3 orbital that exists almost at a diagonal, where one of the lobes kind of overlaps with one of the lobes in the p orbital. So if we're looking at it from the side, you would have an sp3 orbital that almost looks like this. Now, keep in mind that in a tetrahedral molecule, you would have 4 of these arranged in a tetrahedron. And so it's ever so slightly difficult to visualize in 2D, but you'd have one sp3 orbital going horizontal, one coming out at you, one going away from you, and another one sort of going up and to the left. Now these 3 don't really overlap with the p orbital at all, but the one that goes up kind of ever so slightly overlaps with one of the lobes of the p orbital that the radical is in. And that interaction, a slight interaction of an sp3 orbital with one of the lobes of a p orbital, that is called hyperconjugation. Hyperconjugation is where a lobe of the p orbital, electron density in a p orbital, bleeds a little bit into one of the lobes of an sp3 orbital. And when it does that, it spreads charge out, dilutes it in space, and stabilizes whatever is in the p orbital. We've seen this hyperconjugation before. It was hyperconjugation that made more substituted alkenes more stable than less substituted alkenes. In the case of this tetrasubstituted alkene, the 2 p orbitals here are able to leak their electron density into sp3 orbitals on the methyl groups. And that spreads the charge out and stabilizes that charge, whereas that doesn't happen with the p orbitals on this other alkene. The electron density in those stays stuck in that small area between those 2 carbons. So the same idea, the same concept of hyperconjugation, that stabilized alkenes will stabilize radicals too. And because of hyperconjugation, you have a stability for radicals that follows the stability for carbocations, so that a primary radical, a radical on an atom that is just bonded to one other carbon, is the least stable, the most energetic, and the least stable. It's because the p orbital that it's in is only able to leak into an sp3 orbital in one place. A secondary radical would be in the middle. You'll notice that this carbon here that has the radical on it is bonded to two other carbons, so that's the next more stable radical here. And a tertiary radical of these three would be the most stable. So just like with carbocations, the more substituted the carbon is that has the radical on it, the more stable it is. And in this case, that stability is coming from hyperconjugation, where one of the lobes of a p orbital bleeds in to one of the lobes of a neighboring sp3 orbital. Just like with carbocations, the only thing more stable than a tertiary radical is an allylic radical. So we can apply this thinking to B, and here again, you see that this radical on the right, the carbon that has the unpaired electron on it, is only bonded to one other carbon. That's primary, that is the least stable of these. The next one on the left, that the carbon that has that radical on it is bonded to two other carbons. So it is in between. It's definitely more stable than this primary radical. But this tertiary one, in the middle, the carbon that has the unpaired electron on it, the radical on it, is bonded to 1, 2, 3 other carbons. That tertiary radical is the most stable of these three because it has the most hyperconjugation that allows that negative charge to leak out and spread out into the most space. So the big takeaway here is the more substituted a radical is, the more stable it is. That's significant because when a radical knocks into a molecule, it often rips a hydrogen off. But there are lots of hydrogens on these molecules. They bristle off of these carbon chains like bristles on a toothbrush. And so which hydrogen will an incoming radical rip off of the molecule? And an incoming radical will rip off the hydrogen that leaves behind the most stable radical. So just for the sake of comparison, let's say you have a couple different hydrogens. You have one here, and right next door to it, you have one here. If this gets ripped off by a radical, it will steal one of the electrons in that bond, and the other will form a radical on the carbon chain. This, however, is a primary radical. The radical is on a carbon that's just bonded to one other carbon. So that is a very unstable radical, therefore it's unlikely to form. If you try to break that, the hydrogen that breaks off just snaps right back together. Recreates the bond. So in other words, it's very hard to break that bond because the products you get are not stable. Well, if it's hard to break that bond, you could rephrase that and say that's a strong bond. Compare that with this other hydrogen, the green one. If you rip this hydrogen and one of the electrons off to create a radical here, that radical is allylic. It's one atom away from an atom in a pi bond. So this exists in a p orbital. You need parallel p orbitals to create the pi bond here, and so the electrons spread out here through resonance perfectly over all three of those. And so that, because it spreads out that electron, it dilutes its reactivity. It spreads it out in space. And so the hydrogen, this is very stable. This radical is the most stable of the radicals that you could form here. And so the bond to that hydrogen is very likely to break, because if it does break, it leaves behind a very stable radical. Well, if it's likely to break, you could rephrase that and call it a weak bond. So in other words, we're trying to draw in the hydrogens that leave behind the most stable radicals. In this case, it's that hydrogen there, because that leaves behind an allylic radical, a radical that's one atom away from an atom in the double bond. Now, if you go to B, you see pi bonds. Anytime you see pi bonds, look for the allylic positions. We have two of them. We have one on the left and one on the right. You'll notice that the allylic carbon on the left is just bonded to two other carbons, though, and so it's secondary. On the right, this is bonded to 1, 2, 3 other carbons, and so it is tertiary. So this position is not only allylic to 2 pi bonds, but it's also tertiary. And therefore, a radical there would be the most stable of a radical that could form anywhere on this molecule. And therefore, a hydrogen atom at that position is the most vulnerable. That bond to hydrogen is the weakest. It can break the most easily because when it breaks, it leaves behind the most stable product. So this bond to hydrogen, that's the weakest one here. And so you can get a sense of where a radical is likely to form on that molecule. In C, you have a pi bond, and anytime you have a pi bond, the most stable radical will form on the allylic position. Now we have 2 allylic positions. Both of these are 1 atom away from an atom in a double bond. But there is no hydrogen on this carbon. That carbon, all of its bonds are accounted for. 1, 2, 3, 4. All of them are to carbons. And the radicals rip off hydrogens. Hydrogens are very exposed to the surrounding environment. This carbon here is buried in a crowded area, so it's not very exposed. So it's unlikely that a radical will just slap straight into it. It will hit one of these methyl groups first and would react with one of those first. And that doesn't leave behind a very stable radical on these primary positions. So instead, the most stable radical will form on the allylic position toward the bottom. There are hydrogens here. That hydrogen is very vulnerable. The bond to the hydrogen can be broken easily, so you could say it's a weak bond, because if you do break it and you form a radical there, the radical is allylic to this pi bond. It's 1 atom away from the pi bond, and so it's stabilized through resonance. The p orbital that the radical is flying in is going to be parallel to the p orbitals in the pi bond, and so the electric charge can spread out in space over all 3 of those atoms. So because the most stable radical could form at this position, the bond to the hydrogen there is going to be the most vulnerable. And then finally for D, we're looking for the place where the most stable radical will form. The hydrogen that's bonded at that position is going to be the most vulnerable hydrogen. The hydrogen that will statistically be ripped off of the molecule most often by an incoming radical that slaps the molecule in the face. We have a pi bond. Anytime you have a pi bond, look for the allylic positions. That's where the most stable radical could form. We have 2 allylic positions. We have one on the right and one on the left. Both of those are 1 atom away from an atom in the double bond. So they're both allylic positions. But the one on the right is primary. This carbon is only bonded to 1 other carbon. The one on the left is tertiary. It's bonded to 1, 2, 3 other carbons. So not only will this spread out on the left because of resonance with the pi bond, but it will spread out because of hyperconjugation with these other methyl groups. And so the molecule, the allylic position on the left, is able to spread the charge out the most, and a radical forming at that position would be the most stable radical that could form on this molecule. Another way of saying that is that a hydrogen bonded to that position is the most likely to break, because if it does break, the products are stabilized. And so this hydrogen here is the one most likely to be ripped off the molecule as it gets bombarded with radicals around it. So in this video, we've talked about what a radical is. It's an unpaired electron. We've talked about how it is profoundly unstable because the electrons are like little magnets, and so these things are really, really sticky. Radicals will react with the first thing that they slap into. They're very reactive compounds. Nonetheless, so as a class, they're very reactive. Nonetheless, individually, they have a different reactivity. The radicals on the most substituted carbons are the most stable. The most stable radicals of all are allylic. And so when you look at molecules now and you're thinking of them from the perspective of how will this behave in a radical reaction, look for where the most stable radical would form. So either the allylic position or the most substituted position, or both. And that is where a hydrogen is likely to get ripped off in order to create that radical. And we'll see that in mechanisms in future videos for this chapter.